Welcome to episode 14 of writing a 652 assembler in assembly language. The goal for today, last time we wrote a binary search to see if things which looked like symbols were in fact actually keywords. The goal for today is to write some code that will create a symbol table so that if we get an actual symbol, that is our name, something which is not a keyword, we can enter it into the symbol table and return the address of that entry in our tokeval variable. So the value, if we get a name, the value of the that we will return associated with the token name is a pointer to the symbol table entry. Okay, so first, before I begin that, I'm going to go here and make a slight change. I called my function to compare names with the keywords. I called it strcomp because I'm thinking I'm comparing strings. But I'm actually going to change it to keycomp like this. Keycomp, okay? And I'm going to just change all of these as well. And the reason for this is not really just a generic string comparison routine. It's actually comparing only names with keywords. And I'm going to make a small change to it. In particular, I want to make this comparison case insensitive. Okay, that looks like that's everything. All right, I want to make this case insensitive because I want it to be the case that whether you type LDA or LDA, right, or even LDA, that it recognizes this as the LDA opcode, the LDA instruction for the 6502. So to do that, all I really have to do is, when I'm doing this comparison here, before I compare the two characters, I want to change, like my table up here, look up here, is all lowercase. Okay, so all I need to do really is I need to change the characters that are coming from the string, I mean the name that I've read in, the scanned name, to lowercase before I compare them. I don't want to actually go through and change the whole thing to lowercase because I want labels and other symbols in the program to be case sensitive, right? But just for the purpose of checking to see if it's a keyword, I want that to be a case insensitive comparison. And this line right here is what gets the next character from the name. This here is getting a character from the table of keywords. So what I can do is right after I get this, I can just AND it with appropriate value. And I'm pretty sure actually DF, hexadecimal DF, is what I want to AND it with, because that way I can get rid of the bit that makes it a lowercase character. Here is the ASCII table. If we see lowercase a is hexadecimal 61, uppercase a is hexadecimal 41, the difference is that the 2-bit and the high nibble is set for the lowercase character. And what I'm doing here, D is 1101. I'm clearing that 2-bit, although actually I need to set it. That's just so silly because all my things up here are lowercase. So I want everything to be lowercase when I make the comparison. So I just did the exact opposite with what I need to do, but that's easily correctable. Instead of AND, I have here an OR, and this is going to be 20. So I add a 2-bit up there to change uppercase to lowercase, and then I will make my comparison. And this is adding it to the symbol that I've read. Okay, there's actually now a small problem because I have these dots are allowed and also underscores are allowed in symbols. Well, underscores, there are no underscores in keywords, so that's not going to show up. That's not a problem. But dots are allowed in the keywords, as you see right here. So I need to make sure I don't mess with the dots because I don't want to change those, right? Looking back at the ASCII table, dot is 2E. Oh, okay, that's very convenient. So setting the 2-bit here doesn't do anything at all. If I set, it already has a 2 here. So if I just set that bit to 2, it doesn't change the character at all. That's beautiful. That means I don't have to worry about anything. This code right here will work just fine. It won't change a dot at all, but it will change an uppercase character to a lowercase character and then make the comparison. So that should be good. Let's save that and assemble. All right, now I need to, just to make a test, I need to edit my test file. And I'll go down here. And what I'll do is I think I'll just add another line, which is the duplicate of this line. Okay, and I just want to make sure, well, I'll add a couple of variations of it. I just want to make sure that these things all look the same. So save that. Out to the printer. And well, that is no good. Now it's not recognizing anything as a keyword. That's not at all what I wanted. All right, well, the first thing to do in cases like this is just go ahead and get rid of that thing that I added. Okay, and now we have the values that we're looking for here, B3 and da-da-da, okay. So why is this a problem now is the question. Okay, we're taking this character, and this is the one in key comp 0. This is the character from that is the symbol that we've read. It's not one of the strings in the table of keywords. And I can show that because we see right here we're putting 0200 in key comp 0. That was a mistake. Fix that. Okay, so this is just 0200, which is the buffer that contains the symbol read by the scanner. So I think I just need to go through this line by line and see what's going on. So we begin with X is 0. We get a character, the first character originally from the thing. Okay, we were trying to make it lowercase by doing this. We put it in Y. We put it in Y because we're going to compare it to 0 here. We subtract from the symbol character, we subtract the keyword character. If they're not equal, we leave. If they are equal, then we compare Y0. So, okay, so what happens is if we have reached the end of our symbol, there's a null byte on the end. So we would get the null byte, we would put it in Y, and we would compare it Oh, I see. We're doing this to save that character because we destroy it when we do the subtract. So now we're saying that last character we got was, okay, if they were 0, if the two strings are equal, then this would come out equal. The 0 compared to a 0, the null compared to a null is equal. But then we'll say, well, wait a minute, were those equal characters 0? If they are, then we're done. So that's the purpose of that. Y preserves the character from the symbol, and if we're comparing the characters and there's a null there, we compare the null at the end of the symbol with the null at the end of the keyword when we have a match. And it won't branch here because they're equal. Null is equal to null. Then we'll say, well, wait a minute, was it a null? If so, we're done. Then we got a match. Okay. So maybe the thing is, we don't want to do an OR here before putting it in Y, because if we put it in Y, then what we're putting there is not a 0. We've changed that null to a hexadecimal 20. So then when it compares it down here, it'll compare 200. It won't see they match. Right, and also it will be comparing, hang on a second. It's going to load a 0 here, change the null byte into a 20, which is a space. And then it's going to try to compare that against the keyword, which has a null at the end. So it's comparing a space against a null, and it's going to say that's not correct. Oh, that's what's going on. Okay. So what's happening, I see what's going on. What's happening is if, for example, it was comparing LDA with a null at the end to LDA in the keyword table with a null at the end, it's changing all the characters to lowercase. All of the LD and A are changed to lowercase, which is correct. But then when it actually gets the null at the end, it changes the null to a space character and then tries to compare that against the null from the keyword, and they come out as being not equal. Therefore, it says it's not a match. Aha. Okay, so what we have to do is, first off, let's get rid of that. We're going to go ahead and move that. So we have just thinking about the case of the null at the end of the string. We're going to move that here to Y first. And now we're only going to change the character to a lowercase if it is not a null character, if it's a printing character, basically. I mean, the only things it can be is a letter, uppercase letter, lowercase letter, a digit, or a dot or an underscore. Okay, and we don't, actually we do have digits. We have digits we have digits here in these keywords. So let's take a quick look at the digits. And the digits, okay, that's a problem, because if we, no, it's not a problem. It's 30. So setting the 2-bit there doesn't change the digit. Basically, all of these are safe. If we set the 2-bit and the high nibble here, they'll all stay exactly the same. So digits are good, dots are good. That's not the underscore. The underscore is down here. We would change an underscore from 5F to 7F, which would be a delete. But we don't have to worry about that because there are no underscores in keywords, right? So we won't miss matching a keyword because of an underscore. So that's actually not a problem. So what we can do is just take this A. So the only things possible that we have to really worry about are uppercase letters, lowercase letters, digits, and dots. We don't have to worry about underscores because there are no underscores in keywords. And then So null characters. So we'll just say if it's not if it's a null character, sorry, if it is a null character, then we'll branch to a new label here. And if it's not a null character, now we'll go ahead and set that bit to change. And setting the bit here will change uppercase to lowercase. It won't affect dots. It won't affect digits. And it would affect underscores, but that doesn't really matter for us because there are no underscores in keywords, so they're not going to match anyway. Any underscore in a symbol is not going to match. It's not going to be a keyword anyway, so we don't care. And so then we just have to put this here. Key count 0A. So everything works the same until it's a null character. A null at the end of the string. We'll put that null in Y. Well, that was weird. Okay. If it is a null, we skip over this. If it's not a null, we go ahead and set that bit, which the purpose of which is to change uppercase letters to lowercase letters. All right. Whoops. Some mistyping there. All right. And yes, now that's what we want to see. Okay, we still get all of these keyword tokens here, and this LDA of the different, with all the different kinds of capitalization, upper and lowercase, is all B3. That's exactly what we want to see. Good. So that was a little bit of a pain, but we've moved past that. So now we need to go back and work on the symbol table. And I don't know if we'll finish it all in this installment, but we'll start working on it. So the first thing we need for the symbol table is we need to know what is the address of the first byte of memory we have available for dynamically allocated memory, because the symbol table the symbols will be stored in dynamically allocated memory. And that just means we're going to grab some memory at the time we get a symbol and use it. And actually, I suppose I should leave this file. And the idea is that the AS9 is going to be the last file of the assembler, and so whatever is in here will be the end of memory. So let's look at end here. So at the end we have this buffer called inbuff, and it is intended to be 512 bytes long. Right, because what this is this a buffer which contains one block or 512 bytes of data read from the source file. So the first byte, and this is the last thing in our code. So the first byte we have available for dynamically allocated memory is inbuff plus 512. Okay, so what we're going to want to do is actually at the beginning of the program, at the very beginning of the program, the first thing we do is we save the stack pointer. And that's so that when we have a fatal error, we can restore the stack pointer and quit. And also what we're going to want to do here is we're going to want to have a variable which records where that first byte of memory is. And if I could use the editor correctly, that would be nice. So we're going to load A with inbuff. This is the low byte of that buffer, and now we have to add 512 to it. Here, let me put CLC. All right, the low byte of 512, which is a 0, but I'll just leave it as that. And we'll store that in a variable which will keep track of where that next place that we can get memory is. And I'm going to call that variable break. There are historical reasons for that. In really old Unix, the break was had the address of the end of the image of your process in memory. And when your process was swapped out, what was swapped was everything from the beginning of your process memory, which was a location 0 generally, all the way up to break. That was all swapped out. And so the purpose of break was to reduce the amount of memory that had to be copied to disk when you swapped. But I'll use break as the name of my variable because it has approximately the same function, even though there's no swapping here. It just tells where the end of my memory is that I've used so far. Okay, and now we have to load. Oh, by the way, this should also be a immediate value. Okay, now load the high byte of mbuff and add the high byte of 512 to that and store that in break +1. Okay, so this will set up our variable break, which will now contain the address of the first byte that we can dynamically allocate. Okay, and after that, of course, we get our command line arguments and so on. So we just need some place to store this variable break. And it looks like this is going to have to be a global symbol because this is the right place to set the initial value of that break. But we actually want to use it mostly in the file AS1. So I think I will just save that and let's load AS1. And we can just put it right here. It doesn't really matter. Yeah, actually that doesn't work so well because and if we do that, it's not global. I think what I'll do instead well, I could call it entry. Just this Orca assembler is a little bit weird to me how it works. We just have to fake it out somehow. So we could call break an entry point. I mean, it's not really. And then just do that. So now calling break an entry point just means it's globally available to all of the files. But there's no actual code there, it's just these 2 bytes. All right. Yeah, that's what I call faking out the assembler. We're just doing something to make this label available to us everywhere. Specifically, it has to be available in the file AS0 that we just looked at, where we just used it. Okay. So now we're ready to write our little malloc routine. And I was thinking about this off screen, and what I'm going to do, and you'll see why in a little bit, I suppose, is I'm only going to allocate memory in 32 byte chunks. So my little malloc or getmem or whatever subroutine will always get a 32 byte chunk of memory. Nothing and never anything less or greater. And that makes it very simple. And also, I don't ever have to free memory. That's not an issue. I don't have to keep any free lists or anything like that because we allocate memory as we need it for the symbol table, and then we use it to complete assembly of the program. And then after that, we're done, and we're going to exit the assembler, and we don't, we never have to free it and get it back. That just never happens. So it's not really a malloc and free like in C. It's just a way to accumulate the next 32 bytes out of the free memory we have. Okay, so I could call it anything, but just because I lack imagination, I'll call it malloc. Not that it's not really the same as malloc in C, but whatever. Okay, so anyway, what I'm going to do is I'm going to, first off, I'm going to return the pointer in X and Y. So first off, I'm just going to go ahead and get the break. That's going to be the, whatever the value of break is, that's the address of the 32 bytes of memory we're going to allocate. Now I'm going to advance that break by adding 32 to it. Okay, so this just adds 32 to the variable break, which this is a 16-bit addition. So now break is pointing past the last chunk of memory we've used. That's good. So we're basically done there, although we just do have to, we might want to think about the case that that we've run out of memory. I will save this, and let's go look at, I guess, AS9. We have these buffers up here that we're going to use for reading and writing files. Okay, so the memory map we have here is that the disk operating system starts at BF00. Everything after BF00 is unavailable to us because it's either disk operating system or it's memory map IO space. And then we need 4 1 kilobyte buffers for our 4 open files. And I'm right now just assuming I'll need 4 open files, but maybe I won't, and we'll have to change it later. But assuming we need 4 open files, this is our 4 1 kilobyte buffers. And of course, 4 kilobytes is 1000 hex, so it's no surprise that this first one starts at AF00 hex. So this, in other words, we can't, if our break is at this point or later, we can't use it. So what I'll do is I'll just check against this IO buff 0. It's already a globally available number. That's why it has GEQU. So let's go down here. So what I'm going to do is after I add this thing, after I add 32 to break, I need to make sure okay, I'll compare this to IO buff 0. Actually, let me compare the high byte first. That makes sense. I already have the high byte in A here. So I'll compare that to IO buff 0, the high byte of that. Okay, and if it is less, if the high byte of the break is less than the high byte of that, then everything's great. We don't have to worry about anything. Okay, so we'll just exit, returning the pointer to our allocate memory in X and Y. Okay, if our break is somehow greater than, the high byte of the break is somehow greater than the high byte of IO buff 0, then that's very bad. We can't allow that. I actually don't think that's even possible, considering we're only allocating 32 bytes at a time. But we will go ahead and handle the case by saying we're just going to return a 0 in Y and X and Y. That's going to be an indication that no memory is available, as you would expect. Actually, we could do this. It's really only necessary to put a 0 in Y. because any address with a high byte of 0 is a 0-page address, and it's impossible for us to allocate memory in the 0-page. So we can just return a 0 and y, and when we call this malloc subroutine, we'll just check y to see if it's 0 or not. If it's 0, then we didn't get any memory. Okay? Here's the situation that the high byte of the break and the high byte of IO buffer are equal. So now we just need to go ahead and check the low byte of the break against the low byte of IO buff. And if these are equal, then everything's okay. And the everything okay cases go here and return. If they're not equal, I'm sorry, wrong. If the low byte of the break is less than the low byte of IO buff, then that's fine. If it's greater than or equal to, it's not fine. That means there's no memory available. Okay, so here's where we actually determine the address of our new block of memory. Then we advance the break by 32 bytes, by 32, to account for 32 bytes used. And now we just have to go and check that against this IO buff, which is IO buff 0 is the beginning of our IO buffers. And after that comes the disk operating system itself. So we can compare against this to make sure that we haven't run out of memory. And if we have, we're going to set the high byte of y to 0. I mean, set y to 0, which represents the high byte of the returned address. That will mean that we didn't get any memory. Otherwise, we return x and y with this in it, which will be the address of the memory we've allocated. So there's our malloc subroutine. Okay. And actually, it may not need to be entry, because if all of the code that uses it is right here, then it doesn't need to be entry. We'll see. I'll just make it not entry point for now. Okay, so now we have this situation that we have a way to allocate a 32-byte chunk of memory. What we need now is we need the actual symbol table. And the symbol table is going to be a bunch of pointers, and these pointers are pointers to linked lists of symbols. And what we're going to do is hash the symbol to get an index into the symbol table, this list of pointers, this array of pointers. And then, because it's possible that two symbols might give you the same hash value and that therefore be associated with the same entry in the symbol table, the same in the list, that we have to run along this linked list or chain of actual symbols to look for it and find it. All right, and here I'll just bring up a diagram to help explain that. Here's the diagram. So we have a symbol table, which is an array of pointers. And what we're going to do is we're going to take some symbol, for example, mysub or readf or loop23, and we're going to hash the symbol. And there are many ways to hash the symbol. Basically, that means associate some sort of number with this string. I'm just going to add the characters up, right? Add their ASCII values up, and then basically force that to go to the number of things in the symbol table. So if I add these up and it comes up to 157 or something, then what I'm going to do is I'm going to knock off all but the low number of bits that will make it fit into this table. In this case, I have 1, 2, 3, 4, 5, 6, 7, 8 entries in my symbol table. or 8 base entries in my symbol table, I would add these up and then basically get the remainder of dividing by 8, which is the same as removing, just clearing all the bits except for the low 3 bits. And that will then give me an entry. One of these, it will either be a 0, 1, 2, 3, 4, 5, 6, 7. And that will tell me which of these entries goes with my sub. And let's just assume it's this one. Assume that all of these, my sub, readf, and loop23, all go to entry number 1. When we hash it, they all come up. The value that is associated with each of these names is a 1. So it will use this entry. Now this entry is nothing but a pointer. If there are no symbols that go into entry 2, for example, then this will be just a 0 here. But if there are symbols that go to this entry, like here, there will be a pointer. And that pointer will be to a symbol. And a symbol in the symbol table is going to be that has 4 fields. It has a text field, which is the actual characters that make up the symbol. And this is going to be a limited number of bytes. This is not going to be a situation where we have null terminated strings. Instead, this is going to be a certain number of bytes, and we can use up to that many of bytes for the text of the symbol. We'll have 1 byte, which is the symbol's type, and we'll talk a lot more about what it means for a symbol, what a symbol's type means later on. We'll have 2 bytes for the value of the symbol, and then we'll have a 2-byte pointer, which is a link to the next symbol that associated with this 1. All of these symbols hash to 1. So therefore, there's a linked list, a chain of symbols. In this case, there are 3 symbols that hash to entry number 1. The first one is my sub, the second one is readf, and the third one is loop23. And here we have a null. That means that's the end of the list. Okay, so this is the idea of how it's going to work. Now, how it will actually work is slightly different, because what I'm going to do is I'm going to allocate bytes, 32-byte blocks of memory for these things here. This part will not be dynamically allocated. These things will be dynamically allocated. I'll allocate 32-byte blocks. And what I'll do is I'll take those 32-byte blocks and use 2 bytes of that block for the link here. And then the other 30 bytes will be used for 2 of these things. So on one 32-byte block of memory, we'll have 2 different symbols and 1 link going to the next 32-byte block. And the reason for that is just that we save a little bit of memory by not having a 2-byte link for each symbol. But also I have another reason, which we'll see later on, that I like 32-byte blocks. And so it just makes sense that I'll have a 32-byte block. 2 bytes will be the link to the next 32-byte block. And then there will be 30 bytes left over for 2 symbols. And that means 15 bytes for each one of these things. There'll be 15 bytes for a text type and value, and another 15 bytes for a text type and value. And type is 1 byte each. Value is 2 bytes each. So that means that out of the 15 bytes for each symbol, we have 15 minus 3. We have 12 bytes for the text. That means symbols can be a maximum of 12 characters long. And that's actually quite reasonable. A lot of assemblers only allow 8 characters for a symbol, but we will have 12. 12 characters is allowed for the text, 1 byte for the type, 2 bytes for value, that's 15. 2 of those is 30, plus 2 for a link is 32. So the actual implementation will not look exactly like this, but this is the general idea. All right, so what that means, what we need now here is we need a symbol table. And I think I'm just going to go ahead and put that back up. We have all this data, just data, 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 data. I think I'm just going to put it up here. And instead of, here I have in my diagram, I have 8 entries for the symbol table. I think I'll have 64. It should be a power of 2. but I'll have 64 entries, which is 128 bytes. Of course, I'm thinking 256 bytes is a nice round number, so I could do 128 entries, but I'll go ahead and make it 64 entries for now. Basically, it's nice to have a lot of entries here. That means we don't have to do much following these chains of symbols to find a symbol that we're looking for. Yeah, I mean, hey, ideally we could have 16 kilobytes for the symbol table here, and we wouldn't need any chains, but that's not going to work. That we don't have that much memory to spare. So I'll leave it like this for now. 128 bytes for the symbol table, 2 bytes for each entry means 64 bytes total. 64 entries total, so not 64 bytes total in the symbol table. Okay. So let's go down here. So what we can do is when we get a symbol, when we get the scanner reads in a name, something that which might be a symbol, we first are going to call the isKeyW subroutine to see, is it a keyword? If it's not, then it is a symbol. And what we want to do is look it up in the symbol table. And looking it up in the symbol table will either find the entry that already exists or create the entry that doesn't exist. If there's no entry, it will create one. So let's just call lookup. We'll make an entry, a routine called lookup. And this probably will need to be an entry point. Okay. If you remember, the text of our symbol is in the buffer at hexadecimal 0200. All right, and we're actually going to need another string compare function. This one will not be case insensitive though. But yeah, I think I'll get to that when I get to it. So the first thing we have to do is hash the symbol. So we can start with a 0 and A. We can clear carry. We can start with 0 and X as well. Right. Yeah, starting with an here, let's just start with an X and A. We can't really start with the 0 and A. Instead, wait, actually, maybe we can start with the 0 and A. So put that there. We can go ahead and add. Okay, so remember the text of the symbol that we've read from the scanner is stored at this location, which just makes me think up there in the key comp routine, we don't need to actually, when I first wrote that, I was thinking it was kind of general purpose, but it's not, so we could get rid of, we could just do this there as well. And I probably will go do that in a little bit, but for now, I'll just add that. Okay, we increment X. Okay, how are we going to know we're at the end though? That's not so great. Let me look at my 6502, not this one here, this one here. Okay, I can load Y. So what I can do here is actually I can load this thing into Y first, and that if that is a 0, I'll break a loop. The loop will begin right here. If it's not a 0, if it's not, the 0 is the null at the end of the string, then I will go ahead and add it in, increment, and branch back up to lookup 0. Okay, put a 0 in X because we're indexing to the string with X, put a 0 in A to start our hash value at 0. we get the character from the symbol, from the name. If it is a null, then we're done. We're done with the hash value, that is. Otherwise, we add in the character into our hash value and increment x and branch back up here to do the next one. Now what we have to do is we have to AND this with 63. And that will make sure that our value, this hash value, is between 0 and 63. Okay, and then we're going to want to, because this is an entry number, this is a number into the table here, which entry it is, but actually they're each 2 bytes long, so we have to multiply that by 2 with a shift left to get an offset into this symbol table, and then we can move that to x. So now on x we have an offset into this symbol table. All right, so now what we want to do is we want to look at what's at that offset. And actually, I think I would rather look at the high byte. So we're looking at, these are pointers. If the high byte is 0, the high byte of this pointer is 0, that means it's a null pointer, because otherwise it would be pointing to the 0 page of 6502, and that's not possible. I mean, theoretically it's possible, but for our assembler it's not possible. We can't, none of these things are going to be allocated in the 0 page. So if there's a 0 in the high byte, it's a null pointer. And a null pointer means there's no symbol there. Okay, so what we're going to do here is, if it is a 0, we're going to go off somewhere to a label which I'll call lookup 5, and that means I didn't find this symbol in the table. That's what this label is for. The symbol is not found in the table, which means we're going to have to add it to the table. All right, if the high byte is not 0, that means we have a valid pointer. And now what we have to do is we have to start following this chain to try to find the symbol. All right, so we're going to take that high byte that we just grabbed and store it in the code here. This should actually be +2 because it's the high byte. Okay, what we're storing in this place lookup 2 is we're storing the value of this pointer here. All right, and this pointer points to a, it's not exactly like this actually. Maybe it would be better to think of it as something like this. Right, except for where, kind of like that. This is 32 bytes, 15, 15, and 2. So we are pointing at a block of memory which has 2 symbols plus a link for any further symbols in the list. So what we're going to do is check each of these. And this pointer here is pointing directly at the text of the first symbol in this block. And also, for example, if we have this block of 32 bytes and there's a symbol here and not a symbol here, then that means this should just be all zeros here. So a good way to make that happen is when we actually allocate this 32-byte block of memory, to go ahead and zero the whole thing out. That's probably a very smart thing to do. So we'll go back up to the malloc subroutine and zero everything out. but I'll do that in a minute. Okay, so this pointer is pointing at this text here. And yeah, we kind of need our other string comparison here. Here's the one we used before. And I was saying before that this actually is always going to be 200 hexadecimal, so we don't really need that. Okay, and that means we can do this because we don't need this label anymore. So now I just have to go find where it says key comp 0. There it is. So we don't need that. That can just go away. Okay. Don't delete that, just bring another copy in. All right, this first one is the one that's called key comp, and the important thing about that is that it is case insensitive with this right here. We'll call this one sim comp. And this one is not case insensitive. That's really the big difference here. And what I will do is, for now, I'll make this very specific. It's always going to be checking a symbol stored in the buffer at location 200 hex with a random string, well, not random, but arbitrary string here. But if I ever find I need some other string comparison function, I'll just come back and change this to be more general, and probably change the name to strcomp. But I don't really think I'll need another string comparison function, so this ought to be good enough just to call this symbol comparison. And like I said, this is the important thing here, is that this is not case insensitive, it is case sensitive. That's the big difference between these two things here. Okay, otherwise the code is the same. And we want to store the pointer of the thing we're checking at simcomp1. Okay. Yeah, there's the malloc. I'm not going to put the code in there just yet. So this one here is that means it's taking the pointer to this text right here and putting it here, right in place of this FFFF. All right, it makes a comparison. All we care about is whether it's equal or not equal. We don't care about anything else. If it's equal, then we'll go to a label which means I found it, which I'll call lookup for. Right? That one is for not in SimTab. This one is for, well, I'll just say in SimTab. Okay, if this one didn't match though, we still have to go ahead and check the second symbol in this block, And I'm just going to go ahead and check it. If this is all zeros, oh, I just thought of something. There's actually another little error here, but I'll come back to that in just a second. If this is all zeros, then it won't match. So I'll just go ahead and check both of them. And to do that, I have to change this pointer in simcomp plus 2 and simcomp plus 1. I have to add 15 to it, right? Because this is 15 bytes long. So the address of the beginning of this text here is this address plus 15. So I'll just go ahead and load. Well, I'll do a clear carry. Actually, I'll do it this way. Add. Okay, of course, it just occurs to me that I can do this just a little bit more efficiently by branching around an increment. Okay. Yeah, up here in break, when I added the 32 here, I can do that as well. So I don't actually need to do a full 16-bit add because I'm adding a pretty small number here. Basically, I'm only adding a 1-byte number here, so I can add it in, and then if the carry is clear, then there's nothing, the high byte isn't going to be affected. If the carry is set, the high byte is going to be increased by 1. So this is a better way to do that, rather than just doing a full 16-bit add for, yeah, just waste. I mean, we're just using a few more cycles and a few more bytes than we need to, so just do it this way. Okay. So add 15 to that. And go ahead and do the comparison again. Again, if this works, we go to lookup for. We found it. Now, if this, we've now checked this one, it didn't match. We've checked this one, it didn't match. Now we have to look and see if there's a link to go to the next block of memory here. Let's see, where do we have a pointer to this thing? In SimTab 1 plus X. SimTab, this is the pointer. That's the pointer to this right here. It'd probably be easiest if we just we want to remember this value of X somewhere. I think I'll do it like this. So when I get this X here, which is our offset into this table, no, that's not so good. Let's not do that. basically I want somewhere where I have a pointer to this block. So I think instead, here's where I'm accessing that pointer. So I should store that somewhere down here. Okay, I'm storing this pointer in the symbol comparison routine so it can compare. I also want to store it right here. So this represents the pointer to this block of memory and each block of memory in turn, each of the 32-byte blocks. Okay, and the offset of the link field in this is 30 bytes. 15 is 30. So that means here I'm going to load x with 30. Okay, so after this is the situation, we would go down to lookup 4 means we found it in the symbol table. Lookup 5 means we're certain it's not in the symbol table. So right here at this point, we've checked this block, and it's not this one, it's not this one. We need to find this link. So what we're going to do is this right here represents the pointer to the beginning of this. X is 30, so this plus 30 will be the address of this thing here. So that is actually, let's go ahead and make it 31 first. That's getting the high byte of the pointer. If it is equal to 0, that means this is a null pointer, and that means that the symbol is not in the table. Otherwise, this pointer, actually this diagram is wrong, it doesn't point here, it points here to the beginning. Otherwise, this pointer is the address of the next text, the next symbol to check. So we can store that in the symbol comparison function or subroutine. Decrement x. We should actually store it this way. So, it's all the math here. We have a 31 that lets us get it the high byte. This 31 is the last byte of this 32-byte block, this one here. Okay, we see if it's 0. If it is, it's a null pointer and the symbol is not in the table. If it's not 0, we need to store it up here. Here, right here. And that would be actually in symcop 1 plus 2, like this. That's where it's going to be stored. But we have a 31 in x. So actually, we have to make it symcop 1 minus 29. Right? Symcop 1 minus 29. I just put it in here. Here's what we're really looking for. That's what we're looking for. So minus 29 plus 31 would be plus 2. That looks good. Decrement X. Yeah, and now we're going to go have to compare it. Yeah, I think that's just the easiest thing to do here. Compare it to 30. If it's greater than or equal to 30, go back up to lookup 2. That's a problem. We don't actually want to, if it's a 0, if the low byte is 0, that's not bad. We don't want to exit den. Let's see. Let me just leave that alone. What if we had the pointer at 0 page location instead? In that case, do we get a 31 and Y? We would load the 0 page location. Oh, I think that 0 pages doesn't really help my problem here. We don't need to do this now. That's the thing. Don't compare. Just take that pointer, right, and put it up there. So that means take this thing, put up in syncomp there, okay. Lookup 2. So that will copy this pointer, which is pointing here, into the syncomp routine. And now we actually need to put that pointer here as well. And the low byte of the pointer is still an A here. So we can just store it directly. And we copy the high byte from where we just put it to here. Yeah, it's a little bit ugly. It might be cleaner to use 0 page location instead of the self-modifying approach. But I'm just going to leave it for now. Okay, and after we've copied it into SimComp and we've copied this pointer into SimComp and to here, we're ready to now go back up. We're going to loop. Where are we going to loop to? This is where the first one is stored in there. We're going to loop to here. And I'll just call it 1A. Because we've just stored the pointer in the SimComp routine in here. Lookup 1A. Okay, good. So I'll go back up here and check this. Now that will now check the next two symbols here. Now we have the issue of this being a null pointer, like here. And we can check that right here. We're loading that pointer in to store it. If it is 0, we just go to lookup 5, which means it's a null pointer. The symbol's not in the table. Good. So that looks decent. Now, if the symbol is in the table, that we want to do is we just want to return the pointer to that symbol. So whether it's this one or this one, we want to return the pointer to the symbol. So we're just going to grab that pointer out of wherever it is into X and Y. I guess we'll grab it out of the symbol comparison routine because that's, compare it, yes, it's equal, go to lookup 4. Compare equal to lookup 4. So we'll have here load X with simcomplum plus 1, load Y 1 plus 2. In other words, this, where the pointer right here is being loaded into X and Y, and we'll return that. Okay, if it's not the symbol table, we have to insert it into the symbol table. And that I'm going to do next time. Well, we won't do that part today. The last thing I want to do today before I quit is go ahead and, when we have malloc to buffer here, I'm going to go ahead and clear it out, set the whole thing to 0. Okay, so we're loading to X and Y. And this is where we have a malloc 1 is where we don't have memory, we run out of memory. So go ahead and put RTS there. This is where we do have memory, and the pointer is in X and Y. Okay, we're going to store those. Okay, we just getting the break into X and Y. We add to the break. Yeah, actually, I think we don't want to get that now. Oh, but we have to. We have to, because we're about to change it. So just to save that value of the break, we have to do that. Okay, add to the break, store and break. Okay, so after we do that, we're now comparing it. If it fails, actually if it fails, we've just added 32 to the break. We don't want to keep every time, like, okay, if a malloc fails, we're going to just bail out immediately. The program's going to be over. But actually, we don't, just for safety's sake, we wouldn't want to have malloc fail and then call malloc again, call malloc again, fail, and have it keep adding 32 to the break every time, because eventually it'll wrap around and cause all sorts of trouble. I mean, in reality, that's not going to happen. But I just feel like what I ought to do is that I should just store these back, restore the break before I added 32. I think that's a good thing to do. All right, now if the malloc succeeded, then we need to store those store the first part of the break, then load x with 31, load a with 0. This will be malloc 3. Decrement x, branch if it's still not negative to malloc 3. Okay, so we've stored the 32-byte, the address of the 32-byte chunk of memory we're allocating here. Set x to 31, a to 0, start zeroing it backwards in memory from 31, 30, 29, and so on, until x becomes negative. Then we're done. And now all I have to do is, y is actually still, I haven't messed with y, but I have to get x back in, I have to get this value back into x and return. So now we've cleared, zero filled the allocated memory. All right, and then the goal for next time is to figure out what happens if the symbol is not in the symbol table. We have to enter it. And we'll actually then use the malloc subroutine for that purpose. So until next time.